to see how exactly Laplace transform is going to be used directly while solving the differential equations. It is feasible enough to solve a problem directly so that we can understand each and every concept. The problem wherein the problem statement is this, wherein we are given the differential equation d2x upon dt square plus 2 into dx upon dt plus 5x is equal to e raised to minus t. And the objective of this differential equation is to solve it. That means we have to find out what is x of t in time domain. Alright. You already know that the differential equations can be solved by mathematical computations of typical formulas such by calculating particular integral and complementary function. Let us see how we can use Laplace transform to solve this particular equation very easily. The method that we are going to use is we first will convert the differential equation terms into specific Laplace transforms, and then we are going to manipulate the Laplace transform that we get into a form which we know that we can find out the inverse. And after taking the inverse, we will get the required equation or required expression for x of t. So let us solve this particular equation. By using the properties of Laplace transform, we already seen if we know the Laplace transform of x of t as x of s, alright, the Laplace transform of dxt by dt is nothing but s into x of s minus x of t, alright. So this is the property that we have used here as well. So please look at the equation. These are the initial conditions which are given, which will give us the important instructions while we put the values for different initial values here. So while we write the differential equation in this form, x double dash plus 2x dash plus 5x is equal to e raised to minus t, and these are the initial conditions again. Taking Laplace transform on both sides, we will get the Laplace transform of x double dash as s square xs. As this is double differentiation, we will get s square, and then s into x into 0 minus x dash of 0, alright, plus twice of s into x of s minus x of 0 plus 5 into x of s. Now please remember, this x of s is nothing but the Laplace transform of x of t, alright. So what we are going to find is x of s now. We will be finding x of s, and then we will be taking the inverse. The right hand side is the Laplace transform of e raised to minus t, which converts as 1 upon s plus 1. So this is the Laplace transform of e raised to minus t. While we solve this, if you just simplify this particular function, x of 0 is 0, so this cancels out. X dash of 0 is 1, so this term becomes minus 1. And if we take x of s common, we will get s square plus twice of s, this is twice of s that is taken here, and then 5. And this minus 1 is shifted towards right to get plus 1. If you simplify further, you get x of s is equal to s plus 2 divided by s square plus 2s plus 5 into s plus 1. Now, we can directly take the inverse Laplace from here, but we actually don't know what is the inverse Laplace for this function. What is the function whose Laplace is this? We don't know, but now we have to convert this into such a form by typical mathematical manipulations so that we can get the Laplace transform of which we can find out the inverse. So this is done by partial fraction. What is partial fractions? The denominators are separated like these, and the numerators are chosen as unknowns a, b, and c. The degree that we have chosen in each of the numerator is 1 less than the denominator. And when we find out the values of a, b, and c, you will see how we can find out the inverse Laplace. Alright? Because these are the fractions to which we can find out the inverse, because this is of the form the inverse Laplace of this is of the form a into e raised to minus t. And if we further simplify this or manipulate this, we can convert this into sine and cos terms. Let us see how. So this is the partial fraction expansion. When you multiply both the sides of this particular term by s square plus 2s plus 5 into s plus 1. So on the left hand side you get s plus 2, and on the right hand side you will get a into s square plus 2s plus 5 plus bs plus c into s plus 1. Alright. Now if you multiply on the right hand side with the unknowns, you are going to get this function ultimately when you solve. Right. Now you have the left hand side and the right hand side, and you have to match the coefficients of s square, s, and the constant term. So basically there is no s square term present. The coefficient of s square is 0. That means a plus b is equal to 0. That's what we have written here. Twice a plus b plus c is equal to coefficient of s, which is 1. That's what we have written here. And 5a plus c gives you, give you 2. So that is 2. When you solve these three equations for the values of a, b, and c, these are simple simultaneous equations. You get a is equal to 1 by 4, b is equal to minus 1 by 4, c is equal to 3 by 4. This is how you can solve for a, b, and c. Once you get a, b, and c, you can put the values of a, b, and c in the original equation that we have here. Alright, just put the values of a, b, and c. So you get 1 upon 4 s plus 1 plus minus 1 by 4 s plus 3 by 4. We know the inverse Laplace for this. This will be 1 by 4 into e raised to minus t. But how to calculate the inverse Laplace for this particular term? Now remember, the Laplace transform of cos at was s upon s square plus a square, and Laplace transform for sin at was a upon s square plus a square. We can bifurcate this particular term by simple mathematical manipulations as this. If e raised to minus bt is multiplied here, the s will change into s plus b. Alright, here as well. So we will convert the denominator s function as a perfect square and the sum of two perfect squares. Let us see how we can do it. So minus 1 by 4 is taken common. So 1 by 4 upon s plus 1, and here 1 by 4 is taken common. Then we have s minus 3 in the numerator, and in the denominator we get s square plus 2s plus 1 and plus 4. So we have divided this 5 into two parts, 1 plus 4. This 1, this makes this a perfect square of s plus 1, and 4 is itself a perfect square of 2. So these are the two perfect squares. This is how we can bifurcate it. S minus 3 can be written as s plus 1 minus 4. Alright. So this is s plus 1 minus 4 and s plus 1 square plus 2 square. This is how the second term can be written. Now we can separate s plus 1 upon the denominator minus 4 upon this denominator to get two different terms like this. Alright. Let us see how. This is the first term and this is the second term now. So you have s plus 1 upon s plus 1 square plus 2 square and minus 4 divided by s plus 1 square plus 2 square. The inverse Laplace now can be taken. Alright. So the inverse Laplace of first term is nothing but 1 by 4 into e raised to minus t. Second term's Laplace, that means this term, is, because we have shifted s as s plus 1, there must be multiplication by e raised to minus t to the original function. And the cos 2t's Laplace is nothing but s upon s square plus 4. So this is what is present here, and s is shifted as s plus 1. What is the inverse Laplace of 4 upon s plus 1 square plus 2 square? The denominator matches with e raised to minus t sine 2t, but the numerator should be 2, but in this case it is 4. That means we have multiplied by 2 to the original function. But there is division by 4 outside. So basically, last ultimate function, the third term will be 1 by 2 into e raised to minus t sin 2t. This is the final solution for x of t. Alright, I will erase everything on the board so that you can see. So this is the final solution which you can write as x of t. So this is how easily you can find out the solution of a differential equation. The main course of the procedure remains the same. You have to find out the Laplace, convert the Laplace transform function into partial fractions so that you can manipulate the function easily, and then you can just take the inverse Laplace to take the solution. I hope you have understood. I will meet you once again when you call me back. Thank you so much.